Welcome back to CS520. In this session I'm going to talk about event-driven execution. In this model, the program is thought of as responding to a series of events. The events could be external, like a mouse or a keyboard event, or an I/O operation completion. Or events could be internal. For instance, they can be used to introduce abstractions to simplify concurrency. The programmer deals with events by defining handlers. Handlers are just functions designated to handle special events. The system will call a handler for the event when it occurs. At the heart of an event-driven system is an event loop. So the system is running an event loop at the core of the program. When an event occurs, the handler function is enqueued for execution by the event loop. The program terminates when no handler is executing, the queue is empty, and no more events can occur. The program initiation event has a handler, the main function. So let's contrast this with a thread-based approach, which is what we looked at other places during the course. We considered this producer-consumer pattern for threads. Right? There's a thread producing values, they're going into a shared queue, and there's a consumer thread pulling values out of the queue. And we looked at coordinating the interaction of those two threads, coordinating it explicitly by using mutexes and condition variables. Because there were several conditions, right? The producer might be producing faster and the queue could be filled up, in which case the producer waits. Or the consumer could be running ahead and could be looking to pull something out of the queue when there's nothing there. So it would have to wait in that case. And of course they have to signal each other to wake each other up. Well, let's look at how that scenario would look in an event-driven system. We might have an abstraction called a stream, and it hides an internal queue, similar in that sense to the producer and consumer using threads. It's just the queue is explicit in that case. But a stream would also hide the concurrency. For instance, the producer could be run in a separate thread from the event loop. Okay. And the consumer is the one plugged into the event loop. As the producer produces values, the stream announces a data event for the consumer to consume data. And when the producer says there's no more data to produce, then the stream would produce an end event, letting the consumer know to shut down. Let's dig deeper into that picture to see how it really differs from threads. Well, the main thing is that the argument is that it's a simpler view for the user. The user will create a stream, and while creating it, this user will probably have to override the produce method in order to define exactly how data is supposed to be produced for this particular implementation of a producer-consumer. Then the user would define a handler for the stream's data event and a handler for the stream's end event. And then it would just start the stream. That's it. So from this point of view, the user just does four sort of sequential events. Create a stream, define the handlers for these two events, and start the stream. Let's look what the stream does for us then. Stream would create an internal queue, and it would create a thread to call the produce method, insert a produced value into the queue, and announce a data event. And the thread would repeat these 3 steps until the produce method finally says, I'm done. The thread would be blocked when a queue is full, and an end event would be announced when the produce method says it's done. Okay, so the stream definition, would introduce the concurrency through having a separate thread to produce data, and it would also generate events so that the consumer its handlers could be run as the data is produced. Well, what's going on inside the system to support all this? Well, the system again has to provide the event loop. A queue of functions to be called, right? What the event loop is really a queue of functions to be called, and when an event occurs, its handler is placed in the queue. And then there's a thread repeatedly pulling the next function from the queue and executing it. Okay. So this is what the system provides, is that event loop. I guess what I've left off of here is that this thread needs to be blocked. If the queue is empty. Right, when this system thread comes around to pull a function out of the queue of handlers, and there's nothing there, then that thread will have to block until an event occurs. And also, the event loop has to shut down when all the handlers have been executed and no more events can occur. This event-driven model is becoming very prominent. Let me give you a couple examples. In web programming, JavaScript at the core of browsers is based upon an event loop. JavaScript functions are queued up as events occur, and the event loop executes them one after another. Currently there's no concurrency in this model, but you have external events that are happening which drive the event loop. And on the server side, Google's actually defined Node.js, which is a JavaScript implementation developed to implement server applications, and again, it's explicitly built around an event loop. The Google point of view here is that events are actually more efficient than threads and allow you to, from their point of view, allow you to provide more scalable server applications. So this concept of event-driven execution is something that's becoming more and more prominent, and that's why we wanted to take a look at it in this course. Okay, let's stop there.